So with that, I'd like to introduce our next speaker, Nathan Dunkelberger. So Nathan Dunkelberger is a mechanical engineering PhD student in the Mechatronics and Haptic Interfaces Lab at Rice University, working under Dr. Marcia O'Malley. He is studying control implementations for combining functional electrical stimulation with robotics on the upper limb to provide functional assistance after a spinal cord injury. And many, many thanks to Nathan, as he also stepped in at the last minute to give this presentation on Marcia's behalf. Go ahead, Nathan.
Perfect. Thank you for the introduction, and thank you to organizers for setting up this interesting workshop. So the topic of my talk today is user-centric design and control of upper limb exoskeletons. First, I was going to jump into a quick overview of different kind of work that my lab works on. So one of the main focuses in my lab is the development of exoskeletal robots for upper limb rehabilitation, assisting with loss of function either by rehabilitating following neurological injury or providing movement assistance when rehabilitation is not likely to restore function. And we often do this by combining robots that we've designed or are working with other novel technologies, and I'll be discussing some of those in this talk. So I'm going to discuss two different research topics that we've studied recently, including the second, which is my main focus of my PhD. So the first I'll be covering is how we use EMG in the rehabilitation process to engage the user to promote neuroplasticity and recovery. And the second will be how do we combine robotics with a user's own muscles via FES to assist in paralyzed limbs. So for the first topic, it's covering EMG for intent detection and control. And the motivation for this, this is done by former PhD student Craig McDonald. So the motivation for this research is that patient engagement is critical in the rehabilitation process, as many of us know. And intent detection is one way that the patient is actively engaged when they're not able to perform a large amount of the movement by themselves. Often this is done based on kinematic data or by torque production that the user is able to perform. But in cases where patients are more impaired and not able to produce that motion, we need another way of doing this. So one opportunity is to use EMG signals, which are still observed in patients with an SCI. And so looking at this opportunity, we want to use this, but there's still some challenges that need to be approached. One is that when we use EMG, the direct measurements that we take for this are noisy and hard to interpret. Another is that the tuning that we need for this is subject specific. So I'm going to discuss how we approach these challenges. So performing an experiment to identify how we can use this in combination. The platform used for this study is the Mahi Exo2, which is a 4 degree of freedom upper limb exoskeleton. Provides the following 4 degrees of freedom as listed on this page. And the task shown is a target hitting task where the user is trying to hit targets that is either a single of these degrees of freedom of movement or a combination of these degrees of freedom. You can see a visual interface on the bottom right, which shows what the subject sees throughout the experiment in trying to hit either a single or multiple degrees of freedom. And I'll show you how we use EMG to accomplish this. So first, a little bit more about the task is the different motions that we're trying to achieve. On top left, we see single degree of freedom motions for elbow flexion extension and forearm pronation supination. So trying to hit the agonist and antagonist pairs of this, providing 2 different options for each of the degrees of freedom. Then we see a combination of these 2 pairs of degrees of freedom, giving us a total of 4 different targets among the elbow and forearm. Similarly, for the 2 more distal degrees of freedom of the robot, we have wrist radial ulnar deviation and wrist flexion extension. These again can be used for single degree of freedom movements, or they can be combined to achieve another 4 different targets that we want to hit. The way that the EMG intent detection is trained is that a user is in the robot and is asked to remain at rest, and the robot holds them at a neutral configuration. The user is then suggested to move towards one of the degrees of freedom that we were trying to classify for. And the user performs an isometric contraction to the best of their ability. As they're doing this, EMG signals are recorded And this is used to classify the algorithm. Then the user returns to rest and moves on to the remainder of the degrees of freedom, combinations of degrees of freedom for which we're trying to classify. And the design of the classification system, the first layer of it is figuring out the event detection. So first, analyzing whether the user is at rest or whether they're attempting to perform the motion. In the design of the classification, the next step is feature selection. So looking at the EMG signals and what various features are available and actually contains useful information. This is done on a subject basis to get the most useful set for each subject. Then lastly, is trying to understand what the direction classification. So really this is the end goal in trying to identify what the user is trying to do at that time. And looking at the subject, so what we were trying to find here is what is the classification accuracy of the algorithm for achieving different motions. And first looking at able-bodied participants. If you're not familiar with confusion matrices, the way to read these is anything on the diagonal, which is a very dark color, signifies high accuracy, and a 1.0 shows perfect accuracy in classification. On the top, we see single degree of freedom movements. We see that from left to right, we kind of go from most proximal to more distal, and we see that the accuracy for healthy population is very high, meaning about 99% classification accuracy on these single degree of freedom movements. When we look at the multi-degree of freedom movements, see the accuracy drop, but still remain above 90% on average. So we're still seeing pretty good accuracy on those multi-degree of freedom movements for healthy subjects. This was also performed in SCI subjects. And so the intention of this, we expect this to drop in accuracy. And so for the single degree of freedom movements, we see it drop to about 90%, which is still pretty useful in terms of engaging the user in these activities. And for multi-degree of freedom, we see a more significant drop in accuracy down to approximately 60% average. And while we would hope for these to be higher, we still see these as a relative success and that more research should be focused on here. I think this shows promise for future use of EMG control interfaces for robotic rehab in SCI patients. And so the second topic I'm going to discuss is combining FES and robotics in individuals with tetraplegia. This is the focus of my PhD research, so a little bit more about it. The motivation is that many SCI patients require complete assistance with activities of daily living, and two potential assistance techniques are wearable exoskeleton robotics and functional electrical stimulation. However, in their current form, neither is really useful for full functional assistance due to some inherent limitations as shown on this slide. So if we look at exoskeleton robots, so they're very accurate and repeatable and able to produce really high fidelity movements. However, the weight and bulk of them really limit them to a clinical environment in terms of providing full assistance for ADLs. Whereas FES, on the other hand, is very lightweight and mobile. However, it is not able to perform those accurate and repeatable movements needed for ADLs. So we envision kind of a system, maybe as Lucas showed in a previous slide, what they're looking towards is a combined hybrid system with FES and a robot to be able to help perform activities of daily living to kind of get the best of both worlds. So in this process, though, we see additional control complexity in trying to combine these two systems, mainly coming from the side of FES because we're not as familiar with controlling this at a high level. So one is that when we use FES with a user's muscles, it causes instability in state feedback control due to a time delay that's inherent in using functional electrical stimulation. Additionally, when we use FES, just due to the nature of how it works, it causes arm fatigue over extended use. And due to this, we have looked towards a model predictive control framework, which enables kind of us to tackle these challenges by distributing power between the two different subsystems through a cost function that we can modify. Can reduce oscillatory behavior due to the FES time delay by looking more towards the future than looking at only the current state and time. And we can monitor and make adjustments on the fly, hopefully compensating for fatigue. And so to look at a modified or simplified system of this, to first look at experimental results, we look at a single degree of freedom, and this is only focusing on elbow flexion extension with the user. And we can represent this as a pendulum system with two different torque inputs on the degree of freedom, combinatory effects of functional electrical stimulation, and a robotic exoskeleton. And as roboticists, we're very familiar with how to provide torque from a robot, but torque from FES, as I mentioned, is a lot more complicated and tricky to model. So we go through several steps of calibration to come to a predicted level of FES given a control input, but we still have to manage the effects of time delay and fatigue, and also our model may not be all that accurate. So just as a quick kind of overview of how monocular control works, MPC discretely predicts the dynamics over a period of time in the future and selects optimal control inputs so that the inputs and outputs behave in a way favorable to the researcher as described by a cost function that we define. And so in a system like this, I have a typical cost function shown in the bottom right, what we use. So we can look over a trajectory of what we're trying to achieve. We have control inputs of torque from the robot and torque from FES, and we can modify some parameters that we have control over to try to achieve our desired output. So we can look at how much we want to modify our state error. So that's just how far away we are from a trajectory, how much we want to, how much magnitude of input we want from the two different control systems, and how much we want to have those systems change over time. So what speed they're allowed to change at. So with the goal of reducing robot torque, I'm going to just kind of touch on this very briefly. Based on the cost function that we've defined, we can basically prefer to use a majority of the torque from FES compared to the robot. With the same formulation, we can choose to have a smoother FES response, therefore trying to kind of bypass the effects of oscillations due to time delay by making FES behave in a smoother manner and not induce oscillation. And using my new control algorithm, we looked at the effects of this by evaluating the power draw, so trying to reduce the power output of the robot following a functional movement compared to a robot acting by itself. On the right, on the top, there's a power draw metric, and it's normalized, so we can see the new control method on the right. We found a decreased power usage with the new control algorithm compared to using a robot by itself. However, we did see a decrease in accuracy, which is to be expected, but we still think that it's very in a useful range for functional movements for activities of daily living. So this is encouraging for more research on the topic moving forward. And so just kind of to recap, two topics I covered were monocular control interfaces for robotic rehabilitation and hybrid FES and robotic control for functional assistance. Thank you, and I'll open for questions.
Great, thanks so much, Nathan. That was a great talk. I'll start off with a question that is sort of directed at both of these projects that you presented here. Would you mind commenting about sort of how much variation you see in the EMG signals that you measure? We can see maybe a little bit in the classification results you present, but then also in terms of providing the FES with the robotic control. You know, if you have this variation across participants, how do you sort of impact your controller? Are you using some type of training? Is this something you hope to look into more in the future?
Yeah, that's a great question. Inherently, so kind of based on the fact that both of these, especially our surface mounted systems, they're highly affected by the exact way that you mount them. Maybe if you've cleaned the surface before, the amount of resistance in the skin. So often these require a lengthy calibration procedure to actually get repeatable results and to get good results. Certainly something that needs to be accounted for in the future. For example, in my study, which is the hybrid FES and robotics, a majority of the experiment is solely based on the calibration. But yeah, it is a big challenge that's faced in these topics of research.
Hey, really cool work. I have a question on the user experience side. Did you find that people preferred like a certain ratio of FES and then robotic sort of actuation?
Yeah, so so that's actually a pretty good question. And I've done a lot of manual tuning to make sure that it remains comfortable for users. And so the main preference for users is that it doesn't result in oscillatory motion. So I mentioned that that's certainly a possibility with FES. So if we basically lean on entirely FES for the control input, then it results in some oscillatory motion. So trying to tune that beforehand. So there's some manual controller tuning that's done to make sure that it's still comfortable. But in terms of using FES, it really does feel like you're using your own muscle. So there hasn't been much response in terms of, while it's still in the realm of comfort levels, as long as it's comfortable, it hasn't been a big deal between users.
And then a quick follow-up question. Did you have to change the tunings based on whether, I guess, familiarization played a role?
For the FES and robotic control?
Yes, or the EMG. That's sort of a problem that our group is having as well.
Sure. So I can just run the FES and robotics because that's my project, but the tuning that I do actually kind of abstracts out. So I ask users to remain limp, so it's kind of as trying to simulate kind of SCI patients, and the algorithm accounts for how much capability the user is able to put in. So there's not too much difference on that level. In terms of familiarity with EMG, I think we certainly do see some different results if subjects kind of understand what they're doing more because they know how the systems work. And so I think certainly there could be a level of kind of explanation of how these technologies work, and that could help influence and get some better results.
Cool, thanks.